Today we want to talk about inverse trig functions. Here's an outline of what we'll be discussing. We need to recall what inverse functions are in general, and then we need to recall how to graph these inverse functions. After we've done that, then we can talk about what an actual inverse trig function is, and we can look at properties in the graph of the arcsine function, and then lastly we'll look at the properties and graph of the arctangent function. So let's recall the definition from Young's textbook. It says, if f and g denote two one-to-one functions such that f of g of x equals x for every x in the domain of g, and g of f of x equals x for every x in the domain of f, then g is the inverse of the function f. And we say that the function g is denoted by this f to the negative first. And remember that this negative 1 here does not mean 1 over f. This is just a notation that indicates to us that this is f inverse. So let's look at the function y equals x squared. We see that it doesn't pass the horizontal line test because if we put a horizontal line at this level here, at this y value, then it crosses the graph at two different points. So it fails the horizontal line test and it doesn't have an inverse as it is right now. Now what about this function, the function x equals y squared? Well, it passes the horizontal line test, but it does not pass the vertical line test. So we know it's not a function, so it can't be a one-to-one function. And remember back in the definition of inverse functions, they have to both be one-to-one functions. So this graph of x equals y squared can't even have an inverse. Is it possible for us to look at a parabola, y equals x squared, and find an inverse of that function though? Here's a graph of y equals x squared, and notice that the left-hand part of the graph is gray, and the right-hand side is black. Now if we look at only the black side of the graph, then if we do a horizontal line, then we notice that that horizontal line crosses the black part of the graph at only one point. So if I take a domain restriction from x greater or equal to 0, then I have a function that passes the horizontal line test. And we can actually find an inverse for that function. So if we take this black part of the graph and we reflect it about the line y equals x, we get f of x equals square root of x. So the square root of x is the inverse of y equals x squared when we restrict that domain of the function. Now we need to look at some notation of our inverse trig functions. We primarily denote these by two different ways. One way is sine inverse of x, and we use that -1 notational style, or we could write arcsine of x. And each of the other 5 trig functions have the same notation style as the sine function. So the definition of the inverse sine, so we say that arcsine of x is the angle theta such that sine of theta equals x. And we'll get some practice with that definition here. Say I want you to compute the arcsine of square root of 2 over 2. So the arcsine of square root of 2 over 2, if we look back at that definition that I just gave you, is the angle theta such that sine of theta equals square root of 2 over 2. So we know how to find when an angle has sine square root of 2 over 2. If we look at our unit circle, notice that, well, we have pi over 4, the sine value is square root of 2 over 2. If I look over here at 3 pi over 4, it has sine value square root of 2 over 2. So those are the two values on my unit circle that give me sine square root of 2 over 2. And notice here, I've only mentioned one of those values, pi over 4. So let me come back to 3 pi over 4 in just a moment. When theta equals pi over 4, we see that sine of pi over 4 equals square root of 2 over 2. So we have that arcsine of square root of 2 over 2 is indeed pi over 4. Now this question, why is arcsine of square root of 2 over 2 not 3 pi over 4? We'll come back to this question in just a bit. Now let's take a look at a file that I created. So this is a graph of y equals sine of x. And if I draw a horizontal line at y equals 1/2, we notice that in this viewing window, that horizontal line crosses the graph of sine of x at 3 different points. So the graph of sine of x does not pass the horizontal line test. But we can do a domain restriction like we did in the case of y equals x squared. And notice that if we do that, we want to restrict that domain, and usually we want 0 in that restricted domain, so that our graph passes the horizontal line test. Now if I start at -pi/2, and I keep going along the graph, I can keep going until I get to x equals pi/2, because at that point it starts to repeat itself, and we're getting a place where our graph fails the horizontal line test. So our restricted domain will be between -pi/2 and pi/2. Now, our inverse function will switch the x and y coordinates of our function. So when we reflected about the line y equals x, we get that those new endpoints are going to be 1 pi/2 for this one, and -1 pi/2 for this one. And we also have that the inverse function is a reflection about that line y equals x of our original function. So we get that the inverse function is this purple line right here. So this is just a recap of the graph that we just looked at. We have that the graph is this red graph. So we want to look at the domain and range of the arcsine function. We always care about the domain and range of our functions. So the domain of our sine function, when we restricted it, was between -pi/2 to pi/2. So that means the range of our arcsine function is going to be -pi/2 to pi/2. Because remember, when we have inverse functions, the domain and range switch between the two. So that means that since sine is between -1 and +1, we want the domain of the arcsine to be -1 to 1. Now, going back to that question, why is the arcsine of square root of 2/2 not equal to 3 pi/4? Well, notice that 3 pi/4 is a little bit bigger than pi/2. So 3 pi/4 is not in the range of the arcsine function. So we can't have that the arcsine of square root 2/2 is 3 pi/4, because 3 pi/4 is not in the range of that arcsine. So I want you to pause the video and try the following 3 examples. We're looking at the arcsine of the sine of 5 pi/6, the sine of the arcsine of 1/2, and the sine of arcsine of 2. Okay, now that you've had some time to try those problems, let's look at them. We notice that we want to work from the inside of this function outwards. So if I look at the inside, we're looking at the sine of 5 pi/6. Now, if I think back to my unit circle, the sine of 5 pi/6 is going to be 1/2. So now we can plug that in. The arcsine of the sine of 5 pi/6 is equal to the arcsine of 1/2. And if we look at what angle theta has a sine value of 1/2, well, that's pi/6. Now, back to the question we just looked at, why is it not 5 pi/6? Well, 5 pi/6 is not in the range of the arcsine function, so we can't get 5 pi/6 as an output here. We have to look at what's in the range. So pi/6 is, and 5 pi/6 is not in this range. The next question asks us to simplify sine of arcsine of 1/2. If we look at that inside part, we just discovered that arcsine of 1/2 is pi over 6. So sine of arcsine of 1/2 is the sine of pi over 6. And if I think back to my unit circle, the sine of pi over 6 is indeed 1/2. Now, if we want to simplify the sine of the arcsine of 2, what angle theta gives you a sine value of 2? Well, there's nothing on the unit circle that gives you a sine value of 2 because sine is in between -1 and +1. So the sine of arcsine of 2 has no solutions at all. Now I want you to pause the video and try defining and finding the properties and graph of the arctangent function. Okay, so we're going to define this analogously as we did with arcsine, and we see that the arctangent of x is the angle theta such that the tangent of theta equals x. It's a very similar definition to the arcsine function. And if you graphed this, you should have gotten that we have some horizontal asymptotes for the arctangent function at -pi/2 and +pi/2. And this red graph here denotes the arctangent function. If you had trouble with getting that graph of the arctangent function, have a look at this GeoGebra file here. It's similar to the file that we did with the arcsine function, but this is with the arctangent function. So if we look at that domain and range of the arctangent, we see that the domain is -infinity to infinity, which is the range of the tangent function. And the range of our arctangent is -pi/2 to pi/2, which is the domain of our restricted tangent function. Now, if we look at this question, it's a similar question with the arcsine. Why is the arctangent of 1 over square root 3 not equal to 7 pi over 6? Well, the answer to this question is 7 pi over 6 is not in the range of our arctangent function, so the arctangent of 1 over square root 3 cannot be 7 pi over 6. Now I'd like you to pause the video to try the following examples. We need to simplify the tangent of arctangent of 1, also the arctangent of the tangent of 7 pi over 4, and lastly the sine of the arctangent of negative square root of 3. Now that you've had some time to work on these, let's take a look at them. If we want to simplify the tangent of the arctangent of 1, remember we want to work from the inside outwards. Notice that the arctangent of 1 is equal to pi over 4, because the tangent of pi over 4 is 1. Well, we know that also there's another angle on the unit circle, namely 5 pi over 4, that when you take the tangent of it, we get 1. But remember, we have to make sure that our output is in our range. So arctangent does not have 5 pi over 4 in its range. So the arctangent of 1 cannot be 5 pi over 4. Now taking this fact here that the arctangent of 1 is pi over 4, we can now simplify the tangent of the arctangent of 1 is the tangent of pi over 4. And thinking back to the unit circle again, we know that the tangent of pi over 4 is in fact 1. Now simplifying the arctangent of the tangent of 7 pi over 4. If I look at that inside part, the tangent of 7 pi over 4, thinking to the unit circle, I know that that value is negative square root 2 over 2. So then the arctangent of the tangent of 7 pi over 4 is equal to the arctangent of negative square root of 2 over 2. Well, if I look on my unit circle, that value is when theta is negative pi over 4. Now notice that it's not 7 pi over 4 here because 7 pi over 4, again, is not in the range of the arctangent function. Now, if we want to simplify the sine of the arctangent of negative square root of 3, we look at that arctangent of negative square root of 3, and we see that that's negative pi over 3. So then we have that the sine of the arctangent of negative square root of 3 is the sine of negative pi over 3. And if I think about my unit circle, the sine of that angle negative pi over 3 is negative square root of 3 over 2. So what should you be able to do after this video? So at this time, you should be able to find an inverse trig function. So for instance, if we want to look at the inverse cosecant function, then inverse cosecant of x is the angle theta whose cosecant value is x. And you should be able to do that for all 6 trig functions. You should be able to graph inverse trig functions. So when we graphed the inverse sine function, we had to restrict the domain of sine to get a one-to-one function so that we could find the inverse of that function. And we did a similar thing with tangent. You should be able to do that with the remaining 4 trig functions. You should also be able to simplify expressions involving trig functions and their inverses. We did 3 of these problems for the sines and inverse sines, and we did 3 for tangents and inverse tangents, and I think we used sines in one of the examples there as well. Remember, we can mix sines and arcsines and tangents and arctangents in a single expression, like we did in this third example here. We have a sine and we also have an arctangent. One of the things that you need to be very careful with this last one, with simplifying those expressions, you need to make sure that what you're getting is actually making sense. And when I say that, I mean you want to make sure that your output from your arctangent function is actually in the range of the arctangent function. If it's not, then you've done something incorrectly and you need to go back and ask yourself, what is the range of this function? So what could I possibly get as an output?